You've made it to the last video on thermochemistry. Now we're going to look at calculating enthalpy changes for a specific chemical reaction. We've kind of looked at general graphs of endothermic and exothermic changes, but this will be a little bit more specific to a particular type of chemical reaction. And we're still going to use our equation, total energy of the products minus total energy of the reactants. The numbers that we're going to plug into this equation will come off a giant chart. Holy man, look at this thing. This is called enthalpy of formation data. These are the energy changes that occur when these particular substances form. Well, I guess that kind of makes sense. Enthalpy of formation. They're in units of kilojoules per mole. So we've got like the little delta HF. The little F stands for formation. So for example, if I form 1 mole of potassium chloride, we'll release 436.7 kilojoules. Interesting. That kind of makes sense. The little degree symbol up here by my delta H just means at standard conditions, 25 degrees Celsius and about 100 kilopascals of pressure, which is kind of irrelevant to what we'll be using these numbers for. Now, these can be endothermic, exothermic. Most are exothermic. There are a few endothermic. But there is one other type of particle on here that stands out to me. Look at aluminum, liquid bromine, calcium, solid carbon, chlorine gas, chromium, copper, fluorine, helium, hydrogen. I mean, they're all over the place. Look at all these zeros. Neon, diatomic nitrogen, liquid mercury, silver metal, sodium metal. Look at all these zeros. Do you notice that all of the pure elements have an enthalpy value of 0? Enthalpy of formation? We can make note of that. All elements. Delta H F equals 0. Heat of formation is 0 because they occur in nature. If these elements are naturally occurring, it doesn't really take any energy to produce them. There is no energy change. Now I get it. At one point when there were fusion reactions in the sun and the stars, there were major energy changes when these nuclei were produced. We're not going there. If they naturally occur on the face of this earth, their enthalpy of formation value is 0. All elements naturally occurring. Okay, so I'm going to be referencing this chart quite a bit, and you'll probably want to have this handy in your study guide, because here's how we calculate the energy change for a specific chemical reaction. This one is the synthesis of dinitrogen tetroxide. Okay, so we're given the balanced equation. That's handy. We're going to set something up that looks like this. Delta H equals products minus reactants. I have a product, dinitrogen tetroxide. Products minus reactants. Now here's the only thing that you have to be a little careful of. We mentioned that these enthalpy of formation values are in units of kilojoules per mole. Kilojoules per 1 mole. If you have a coefficient in your balanced equation, that's a ratio of moles. So I need 2 moles of the nitrogen dioxide. Let's just multiply by 2. Products minus reactants. Multiply by any coefficients in the balanced equation. Now the numbers that I'm going to use just come off that chart. So I'm going to look them up. N2O4, his enthalpy of formation value is 9.2. And technically it's kilojoules. These are all in units of kilojoules per mole minus 2 times NO2. I'm going to look him up. 33.2. Plug and chug, right? Put this in your calculator. 9.2 minus 66.4, negative 57.2 kilojoules. Done. That's it. Ooh, that's not bad, huh? Now, you don't have to set it up with the formulas in there. I kind of like to do that because then I know I have everything in the right spot before I go to the chart and start looking up the numerical values to substitute in. Common mistakes, people go reactants minus products, or they'll forget the coefficient in the balanced equation. We got to multiply. Let's try another. These are kind of fun, huh? 2 and 3. I like these. They're adorable. We've got the balanced equation for the synthesis of iron oxide, rust. Iron will slowly oxidize into iron oxide if left untreated in the open air. Enthalpy change, again, just a fancy word for energy change. So I'm going to have something that looks like this. Products, 2 times the iron oxide, but that's my only product, minus, now I want total energy on the reactant side. It's going to be 4 times iron plus 3 times oxygen. Total energy of the products minus total energy of the reactants. Now we'll sub in those values. Okay, so I'm going to go to my chart and look them up. Iron oxide, negative 824.2 minus 4 times iron. Well, what do you know? It's a 0. And could it get any better? Sure can. 3 times 0. They're elements. They're elements that occur in nature. Solid, iron, O2, oxygen, diatomic gas. It's their elemental state in nature. Ha! This is great. So I'm going to plug this in. And really, it's just 2 times the negative 824.2 minus 0. Negative 1648.4. And then these are in units of kilojoules. Exothermic. Cool. Okay, now watch this. What if we want to reverse that? What if I want the decomposition of the iron oxide? So if I reverse that equation, 2O3, the iron oxide decomposes to form the iron and the oxygen, O2. Now you can plug it in if you want to, but look, it's really just going to be like the opposite here. I would have delta H equals, on my product side, 4 times 0 plus 3 times 0 minus my reactant, 2 times the iron oxide, negative 824.2. Well, look at this. I'd end up with like 0 minus negative. It's the same numerical value. It's just positive. Well, look at that. Something to make note of. Synthesis. Synthesis reactions where bonds are formed. Forming bonds will always be exothermic. And you'll get that negative delta H. Forming bonds is exothermic. The opposite is true of a decomposition. During a decomposition, You're breaking bonds. Breaking bonds, which always requires energy. The iron oxide is a very stable compound. You've got to add a lot of energy to break that bond. It will always be endothermic. And you'll get that positive delta H. Now the other thing that's kind of interesting too, which of these is favorable in nature? The rusting process? Or does rust just spontaneously turn back into iron and oxygen? And now you're probably thinking, oh yeah, this is spontaneous. The negative delta H, the exothermic change is more likely to be spontaneous. Nature favors rusting. But the second, the decomposition, this is not spontaneous. In nature, if you got like a rusty nail, it doesn't just go back to its original iron. That would be a highly endothermic process, and it would require a lot of energy input. So look at that. This just all comes full circle. I love it. All right, so a couple other ones that we should mention. Check out these last few. The enthalpy change for a combustion. We're going to need the balanced equation. So we've got our C2H5OH. Combustion means we're going to react with oxygen, diatomic, to produce carbon dioxide and water. I'm going to need to balance this. Oh, let's see. 2 carbons. There's really a total of 6 hydrogens. 3 times 2 is 6. And then my oxygen. All right, here's 4 and 3. We need 7. How about 6 and 1 for 7? All right, now let's plug this in. And if we're getting good enough, we don't have to show like the elements or compounds. You can go to your chart and start plugging in the numbers. Just be careful that we start with the products. We're going to have 2 times carbon dioxide. I am looking up carbon dioxide as we speak. Negative 393.5 kilojoules per mole. I got to multiply by 2 because there are 2 moles in my balanced equation. Then I'm going to add the water. All right, so this is going to be 3 times. Now we got a decision to make here. On my chart, I see water in both the liquid phase and the gas phase. But you remember how we kind of said that typically in a combustion, the water is formed as, whoopsie, water vapor, not liquid. Let's do that. Let's get that out of there. Let's use this as water in the vapor phase. Gas. So I'm going to look up water gas and say negative 241.8. Products minus reactants. So I have that ethanol, negative 277.7. plus 3 times oxygen, and it is 0. It's an element. It occurs in nature. Now sometimes when I get a lot of particles, I like to simplify the products and the reactants. Obviously you don't have to, but there's a lot of negatives going on, and sometimes it's easy to miss something. So I'm going to plug this all in and simplify that to negative 1,512.4 minus the negative 277.7. It's so easy to miss, like that minus negative, but this is still exothermic. 1,234.7 kilojoules. Still exothermic. make note of this. It's a combustion. I mean, didn't we say back in the reaction unit that a combustion means something is burning? A combustion should always be exothermic. The combustion. Exothermic. Always, always, always. Now, other reactions, like maybe 5 and 6, single replacement, you never know. But the combustion will always be exothermic. The decomposition is always endothermic. And then the synthesis will always be exothermic. 5 and 6, yeah, with a replacement, you just kind of have to plug them in. We are going to do 5 and 6 in class. They're awesome little reactions. Check this one out. Delta H equals products. My aluminum oxide, solid, negative 1675.7, plus 2 times iron. Now notice here that they have the iron listed as a liquid. As I'm looking at this chart, I only see iron solid because its normal phase is solid. So let's use the solid, and then that would be 0. Minus reactants, iron oxide, negative 824.2, plus 2 times aluminum solid, 0. Okay, so we got, this one's not too bad. Negative 1675.7, and then be careful, minus negative 824.2. Exothermic, negative 851.5 kilojoules. All right, so the liquid thing there. We're going to run this one in the lab, and if I can run this on a large scale and release a ton of energy, we might be able to get the iron molten. We would essentially melt the iron if I release enough energy. How exciting would that be? And then finally, this last one. We're going to run this one too in class. This one's kind of cool as well. Delta H equals. You just have to be organized with these things. Products. 2 times ammonia. I am looking up ammonia, negative 46.1. Plus, now notice here that this one is listed as liquid water. Whoa, that's a star. So I'll look up the liquid water. Negative 285.8. So it's a little bit different than the combustion. Then I used water vapor. And then I have barium chloride. Negative 860. Okay, so here are all of my products. I'm going to need some more room. Products minus reactants. Okay, we have 2 reactants. Minus. I've got 2 moles of that ammonium chloride. Negative 314.4 plus the barium hydroxide. Oh, I think I can squeeze it in here. Barium hydroxide, negative 998.2. There's a lot going on. Products minus reactants. Multiply by the coefficients in the balanced equation. So I think for sure with this one, I'm going to simplify these 2 quantities. So I'm going to plug all this in. 2 times the negative 41.1 plus 2 times negative 285.8 and the negative 860. Negative 1,523.8 minus, and then my second quantity here, let's plug this in. 2 times negative 314.4 And the negative 998.2 is a negative 1627. So we have to be careful here. We have minus a negative. Aha! This one's going to be endothermic. 103.2 kilojoules. This one's positive endothermic. We're going to run this one in class, and the endothermic reaction will absorb energy